This is the third video in a four-part series for an engineering framework for food safety. The video before this discussed at length the framework for or an engineering framework for studying microbial safety. This one is going to talk, it's a very short one that's going to talk about a framework for chemical safety or framework for studying chemical safety. And the video after this would basically summarize this entire series of four videos on engineering framework or an engineering framework for microbial and chemical safety. So as I said, we have already discussed an engineering framework to study microbial safety. So this time we are going to talk about an engineering framework to study chemical safety. So what do we mean by chemical safety? Chemical safety aspects during a food process may include the formation of a number of compounds such as acrylamide during this frying process, or a formation of heterocyclic amines. In both cases, the formation of those compounds are carcinogenic, meaning they can cause cancer, and so we would like to know how much and how to reduce it. Can we discuss a physics framework for such chemical safety so that we don't have to come up with ad hoc ways of handling each situation? We'll see that this framework follows what we did for microbial safety, but of course it's a lot simpler because the chemicals are more passive compared to the microbes. The physical description of the carcinogen physics or the physics of chemical safety can be nicely included in the transport equation, where the concentration really refers to the concentration of the carcinogen as a species. So in this case, in meat cooking, it will be the concentration of the heterocyclic amines, or in case of deep frying, it would be the concentration of the acrylamide. So those can be nicely incorporated in the transport equation. But the rate of reaction, as would be included in this source term that has the rate kinetics, the rate is definitely going to depend on temperature. So the temperature will have to come from the process physics. So that is how the carcinogen physics and the process physics are coupled. And together, the process physics with the carcinogen physics form the framework, the physics framework for chemical safety prediction during, let's say, a cooking process. Now we'll see two examples of this overall framework to kind of make things more obvious. So here is the first one, acrylamide formation in a French fry. And acrylamide being carcinogenic, we want to know how much of it forms and when and how to reduce it. So here is a cross section of a French fry, and again we want to know where does the acrylamide form and when. So the physics in this case is simply the rate kinetics of acrylamide formation given by this equation. Again, this is from the work of the authors noted here. Of course, this rate kinetics can be thought of as belonging to the transport equation here, where the rate would be calculated. It's this term here would be included as the rate, and we may have a small diffusivity for acrylamide, and if this is a solid, if there's no other velocities, then we might drop this term. So then the framework, the transport framework for acrylamide concentration as a species would be able to handle this kind of a complex change in acrylamide concentration with time and position. However, you notice that this term has temperature in here. Of course, the rate of reaction depends on temperature. Where would I get temperature? So we would get temperature from process physics. So in this case, what is my process? It's a frying process. So what is the physics of a frying process look like? It describes heat transfer, moisture transfer, oil transfer, but all of these can be done. And if this is done, then I get temperature from the heat transfer equation, and that temperature is what is plugged in here. So this way, my physics for the carcinogen formation and the process physics are coupled to get overall safety prediction by their combination. And this will provide exactly how much acrylamide is formed at any location and at any time. So this shows an example of the physics framework for chemical safety in this case, or understanding chemical safety, combining the physics framework for the chemical or the carcinogen with the physics framework for the process. Here is a second example of the overall safety prediction framework in case of chemical safety. In this case, it has to do with heterocyclic amine formation that happens in meat cooking at high temperature, and of course these heterocyclic amines are carcinogenic. So we want to know how much forms and how we can reduce it. The physics of the carcinogen again is simply the carcinogen kinetics. So in this case, it was modeled in one study as a first order reaction, but notice it's a generation. So it's a positive K. So it's a generation of the carcinogen. In our transport equation for the carcinogen as a species, so this is the transport equation that gives concentration of carcinogen as species, the source term will come from this reaction. In fact, the source term is simply K times concentration of the heterocyclic amine. But as you can expect, the rate constant in this reaction is going to depend on temperature. So the temperature has to come from the process physics. So the process physics in this case for meat cooking can involve heat transfer and moisture transfer in the meat. So, and it can be quite complex, but nevertheless, it has been done at various levels. So from the process physics, we get the temperature, and that temperature gets plugged into the rate constant. This is how the process physics is coupled. The process physics is coupled with the carcinogen physics. By combining these two, I can get the formation of carcinogen. So in this case, blue is low and red is high. And since it's being heated from the bottom, you expect more carcinogen to form with cooking at the bottom, so the bottom turns red. So you can see I have safety prediction that gives me carcinogen concentration as a function of location and time in the food, and the framework we used is treating the carcinogen as a species. So we use a species transport equation. It might have a velocity term if the carcinogen is being carried by the liquid that could be moving inside the food. That could give me the velocity here. Diffusion of the carcinogen may be small, so we might be able to drop this, but it's combining this carcinogen physics with the process physics that gives me the safety prediction. So that's again my example of the physics framework for safety that combines chemical or carcinogen physics with the physics framework for the process. So we're going to look at that same framework that we have been discussing in slightly differently. Here I'm going to add a small step at the end, small but important step at the end, that will make this framework look like the framework for, let's say, the physics framework for quality. So to make the point that quality and safety, they all follow the same general framework. So to get started with, first we need the local kinetics or the kinetics of formation of the chemical. So why the word local? Because the formation of chemical at any location just depends on the temperature, let's say, of that location. And the temperature could be different at other places. So it depends on the temperature at that location. So it's the local kinetics. And then because it depends on the temperature, we need to provide that temperature. And that temperature comes from the process kinetics. So that is how the local kinetics gets combined with the process kinetics. This is what we already have said. But the extra step that I want to talk about here is once we combine local kinetics and process kinetics, then it gives, let's say, carcinogen concentration everywhere. And then we need some added but very important information. For example, from a safety standpoint, it could be where the maximum amount is formed. For example, in that meat grilling from the bottom, the maximum would be formed on the bottom surface. Or we may need the total amount formed. So summing either the total amount or the average amount or the amount at the location where the concentration is highest. So we need to extract this kind of critical information. So as a final note then, we have a physics-based framework for food chemical safety that combines the physics of carcinogen formation, which is a transport equation or transport framework for the carcinogen, with the process physics, and extracts, at this last step, extracts the most critical information, that is, let's say, the total amount of carcinogen. So this is what we mean by developing a framework for chemical safety prediction.